So for the material is we are going to use AAA alkaline battery and 2 pieces of neodymium magnets. We will use copper wire. Copper wire must not have enamel and it must be bare copper wire. And lastly, we will use metal rod. Metal rod is for we circulate the copper wire to the metal so that it will make a shape of a coil. Firstly, we will attach the copper wire to the metal rod with a tape, as you can see this. So the next step, we will circulate the copper wire on this metal rod. Then there you have it, a coil. A copper wire coil. Next, after you already ready with your coil, the next step is to attach your magnets to the battery. So first thing first, you need to know which one is the north and south. Now I'm attracting this part of the battery. So the first thing you need to do is to know whether this magnet will attract with this side of magnet. So let's see. Okay, looks like it repels to each other. So the main thing here is I want to say is make sure that the top side, the positive side of the battery is facing north, the magnet facing north, and the negative side of the battery also facing north, which is repelled to each other, right? So yeah, it must be like this so that it can moves in the coil later. So there you have it for the material. It is already set. One copper coil and one battery, alkaline battery, and 2 magnets. So now we will test the experiment for the electromagnetic train. So make sure you enter the battery on the correct side. So here we go. Look for the movements. Yeah, you see that? It gets out by itself. So if you want to go on the reverse side, make sure to change the direction of the battery. So that's all for today. So I hope you enjoy. So this is the experiment of the electromagnetic train.
We will put 2 basic principles of electromagnetics and magnetism to work to create an electric train. The first is the magnetic field created by a solenoid. A solenoid is simply a coil of wire wrapped in a tightly packed helix shape. Solenoid can be used to generate a nearly uniform magnetic field similar to that of a bar magnet. When the solenoid is connected to a voltage source, a current is provided along the wire. The current, which is gone through this circularly looped wire, results in a constant, ideally uniform magnetic field through the center of the coil of wire. Thus, an electromagnet is created. The strength of the magnetic field, B equal to mu and L, is proportional to both the number of turns of wire per unit length, N equal to N over L, and the strength of the current passing through. One way to confirm the magnetic field lines for a solenoid is by using Ampere's right-hand rule. Point the thumb of your right hand in the direction of current along a wire, then curl your fingers inward. The direction of your curled fingers gives the direction of the magnetic field. The magnetic field radiates outward in a circle, with the magnetic field strength decreasing as you go farther from the current carrying wire. Simply Follow along the curve of the solenoid with your thumb and confirm the direction of the magnetic field will always be through the center of the solenoid. The second principle utilized is the premise of magnetic poles. A magnet always has a north and south pole. The opposite north and south pole attract to each other and same poles, N to N and S to S, repel. A magnetic field can also interact with magnet and cause a force upon the magnet inside the magnetic field. How do these two principles connect to create an electric train? The key is that the magnets are neodymium. Neodymium magnets are magnets made up of combination of iron, boron, and neodymium. These are all located on the periodic table of elements. These three materials are melt, combined, and then pass through a very strong electromagnetic field to magnetize them. This combination of conducting materials allows neodymium magnets to conduct the electricity. Most other magnets, such as ceramic magnets, are non-conducting. Ceramic magnets are made up of a combination of powders like iron oxide and strontium carbonate. Based on the materials that make them up, ceramic magnets do not conduct electricity. Thus, when the neodymium magnets are attached to either end of the battery and resting on the uninsulated copper wire, a local circuit is made along the length of the battery. The circuit is made from the positive terminal of the battery into the magnets through the copper wire of the solenoid and back into the magnets on the negative terminal of the battery. These local circuits provides the current to create the magnetic field within the solenoid. Next, the geometry of the battery is such that the magnets are on either end of the battery. This causes the magnetic poles of the magnets attached to the battery to simultaneously be pushed in out of the local circuit, depending on which magnet you are looking at. This force causes the battery train to move. However, as the train moves, it creates a new localized circuit that perpetuates the motion. But not to forget that the magnets must be oriented such that the same pole is facing each other. This allows the force to be in the same direction and to combine. Otherwise, the force will cancel out and the train will not move. If both magnets flip to have the other dipole facing out, the force will reverse direction.
For real-life application, maglev, also called magnetic levitation train or maglev train, a floating vehicle for land transportation that is supported by either electromagnetic attraction or repulsion. Maglevs were conceptualized during the early 19th century by American professor and inventor Robert Goddard and French-born American engineer Emile Bachelet, and have been in commercial use since 1984, with several operating at present and extensive network proposed for the future. Maglev incorporate a basic fact about magnetic force, like magnetic pole repel each other and opposite magnetic pole attract each other. To lift, propel, and guide a vehicle over a track or pathway, maglev propulsion and levitation may involve the use of superconducting materials, electromagnets, dimagnets, and rare earth magnets. For results, we can see a better result than in this video if we are using a long bare copper wire. A bare copper wire without enamel is really hard to find at shop, so we decided to take the copper wire from the telephone wire on our home. The wire that we get is not long enough, the result will not, showing 100% based on reference. For the analysis, an electric current flows through a coil through a neodymium magnet, and the coil will be an electromagnet only in an area between the magnet and the magnet. The electromagnet and the neodymium magnet pull repel each other at one side. The other side pull against each other. They work in the same direction, and it becomes a big force. The phenomenon also continues at a movement destination. For summary, we applied both of our objectives in our experiments. As a result, our experiment was quite a success, but the results can be better if we use a long bare copper wire.